Section 7.6, Integration using Tables and Computer Algebra Systems. The region bounded by the curves y equals arctangent x, y equals 0, and x equals 1 is rotated about the y-axis. Let's find the volume of the resulting solid. So let's try drawing what arctangent looks like, or tan inverse. So it should look something like this. We only need the part in the first quadrant right now because this thing is bounded by y equals 0 and x equals 1. So let's draw x equals 1. How about something like that? And I can say over here is at 1, and this is the line x equals 1. So then this is y equals arctangent. Okay, and now we want to rotate it around the y-axis. So we want to rotate it around over here. And that means it's going to end up something like this. So our rotation obviously goes all the way around. I'm just drawing it flat, so you only see the 180-degree rotation, but it becomes a solid object. So if we want to find the volume of the solid, what we could do is we could take a whole bunch of slices like this, and you can see there would be washers, and then each washer would have a tiny change in width dy as we stack up on the y-axis. But if we want to keep everything in terms of x, then we could instead draw shells, and then we could stack up shells along the x-axis going outward. So let's do that method. How about I draw, or attempt to draw, little shells? So I'll start with a rectangle, and then try drawing the shell. Okay, so that's roughly the shell. Notice that the radius of the shell is the x value that over here that goes outward, and the height of the shell is the y value, which is going to be arctangent x. So that means that the volume of our solid of revolution is the integral from 0 to 1 of 2 pi times the radius x times the height arctangent x. So it's a pretty simple integral to construct, and it looks pretty simple to evaluate if we were to know what the integral of x times arctangent x is. So there should probably be a formula somewhere though, because that looks so elementary. So how about we take out our table of integrals? And let's go down to table of integrals in our reference pages. Here it is. So we have some basic forms, then some other forms. Let's keep going until we get to trig forms. Here we go. So we're looking for something with arctangent x, or inverse trigonometric forms. And here it is, number 92. So it looks like the integral of something times tan inverse is something squared plus 1 times tan inverse minus something over 2 plus c. So let's use that. So we get, let's repeat what formula 92 said really quick. We see that the integral of u times tan inverse is equal to u squared plus 1 over 2 plus tan inverse minus u over 2 plus c. So that means that our volume is equal to 2 pi times the integral from 0 to 1 of x tan inverse x dx, which is equal to 2 pi times x squared plus 1 over 2 times tan inverse of x minus x over 2 evaluated from 0 to 1. So our 2's cancel, and we get pi times x squared plus 1 tan inverse x minus x. And we get pi times 2 tan inverse of 1 minus 1, because there's no contribution from 0. So that becomes pi times 2 times pi over 4 minus 1, which is half pi squared minus pi. Let's use the table of integrals to find this integral. So it looks like we should be looking for something squared over a constant minus something squared. So let's go back to our table of integrals. Let's go back up away from the trig page. So that's u squared minus a squared, and here's a squared minus u squared. So if we let a squared equal 5, then it looks like we can use formula number 34 over here. We'll just have to do a quick substitution to make the 4x squared become a u squared. So let's put that back. Formula 34 tells us that u squared over the square root of a squared minus u squared is equal to minus u over 2 times the square root of a squared minus u squared plus u squared over 2 times sine inverse of u over a plus c. And it shouldn't be too surprising that there's a sine inverse in here, because it kind of looks like this would be a good trig substitution problem. But anywho, we let u equal 2x, and then our integral x squared over the square root of 5 minus 4x squared becomes the integral of u over 2 squared divided by 5 minus u squared. And then du is a 2 dx, so that means du over 2 is equal to dx. So we get 1/8 times the integral of u squared over the square root of 5 minus u squared. And we use our formula. We get 1/8 times minus u over 2 times the square root of 5 minus u squared plus 5 over 2 sine inverse u over root 5 plus c. So even though 5 is not a perfect square, we still let 5 equal a squared so that we could do the formula with a equals root 5. So we get minus x over 8 square root of 5 minus 4x squared plus 5/16 sine inverse of 2x over root 5 plus c. Okay, let's look at our table of integrals for this integral. So we go back to the trig section. And we're looking for something with something times sine. So it looks like we don't have u cubed exactly, but we do have a way of taking u to the n times sine and reducing it into something with cosine. So then we would take the x cubed sine x, we would end up with, it looks like, x squared cosine x. So we need a formula for that. But looks like the next formula has cosine, so we would use this one to reduce it further, and that would reduce it to something times sine. And then it looks like x times sine x, well, we could use formula number 82 for that, and then we would finish everything up. So let's use those three formulas. First, we'll use 84 to reduce sine into something with x squared cosine. Then we'll reduce x squared cosine into x sine, and then we'll finally evaluate x sine. So by formula 84, we get that the integral of x cubed sine x dx reduces to minus x cubed cosine plus 3 times the integral of x squared cosine. And then by formulas 85 and 82, we get that the integral of x squared cosine is equal to x squared sine minus 2 times the integral of x sine x dx. So that becomes x squared sine x minus 2 times sine x minus x cosine x when we use formula 82. How about we use k for our constant? That way we can use c later. So we get that the integral of x cubed sine x dx is equal to minus x cubed cosine x plus 3x squared sine x plus 6x cosine x minus 6 sine x plus c, where c is 3 times our constant k. Let's use the table of integrals to do this one. Well, you might have noticed in our table of integrals we didn't have any expanded quadratics like this. We only really had squares. So what we should do first is complete the square inside of that square root. So let's look at x squared plus 2x plus 4. That's equal to x squared plus 2x plus 1 minus 1. We'll just add and subtract 1 because that's half of the middle term, the middle coefficient squared. And we keep our plus 4. So then we'll factor our new perfect square, and we get x plus 1 squared, and then minus 1 plus 4 is plus 3. So it looks like we should let u equal x plus 1 over here. That way we just have u squared. So if u is equal to x plus 1, that means that x is equal to u minus 1, so that'll help us get rid of the x. And we get the integral of x times the square root of x squared plus 2x plus 4 is equal to the integral of u minus 1 times the square root of u squared plus 3. So we can distribute and get two integrals. One is u times u squared plus 3, and the other one is just u squared plus 3. So you might be thinking, okay, well, one is more complicated than the other one, but the more complicated one is actually easier to integrate because you could just do a u substitution and then you've got your du right next to it. Whereas over here, if you substitute for u squared, then there is no u nearby. So this is the one we're going to want to look at in our table of integrals. So first, let's do a u substitution for this one. We already used u as a letter, so how about we use t for this one? Let's let t equal u squared plus 3. So then dt is 2u du. So that means that our integral u square root of u squared plus 3 becomes half of the integral of square root of t dt, which is t to the half, so that's half times 2/3 t to the 3 over 2, which is 1/3 u squared plus 3 to the 3 over 2. Okay, now let's look back at our table of integrals and see if we can find one that's good for this. So get out of the trig section. Not just a plus b, we have a square root, and ours is first, and it's plus. Here we go. So it looks like formula number 21 is what we want. Square root of a squared plus u squared. In this case, a will just be the square root of 3. So a squared is 3. Don't think we need this. So we'll use formula 21. Which says that the integral of the square root of u squared plus 3 is equal to u over 2 times the square root of u squared plus 3 plus 3 over 2 times the natural log of u plus square root of u squared plus 3. And this formula seems to probably make sense because this looks suspiciously like one of those hyperbolic trig identities, and this looks like a candidate for a trig integral. So we get that the integral of x times the square root of x squared plus 2x plus 4 is equal to 1/3 times x squared plus 2x plus 4 to the 3 over 2 minus x plus 1 over 2 times the square root of x squared plus 2x plus 4 minus 3 over 2 times the natural log of x plus 1 times the square root, oh, sorry, I forgot my plus, plus the square root of x squared plus 2x plus 4. Okay, let's do the same integral now with a computer algebra system. So how about we pull up Wolfram Alpha, and we will type in integral x square root x squared plus 2x plus 4 Oh, I didn't even notice I typoed. So I thought I was using Indian rupees. Maybe I wanted to. Okay, that looks a little bit better. So now we have our indefinite integral. Let's pull that up. Let's see if I can get it. Okay, cool. Notice that this is a little bit different than the formula we got. It has a sinh inverse in here, a hyperbolic trig function. But if we go down and we look at some of the alternate forms, we can see this form over here. So let's pull that too. Tried to. Or not. Well, let's at least make it a little bigger. Okay. So let's see if we can make this look like our other form that we already calculated. Well, you might recall that we have a formula for arcsinh. And it's ln of x plus the square root of x squared plus 1. That's from section 3.11. So that means that arcsinch of the, not x now, I want to plug in for x, of the square root of 3 over 3 times 1 plus x is equal to the natural log of the square root of 3 over 3 times 1 plus x plus the square root of 1/3 1 plus x squared plus 1, which is equal to the natural log of 1 over rad 3 times 1 plus x plus the square root of 1 plus x squared plus 3, which is equal to the natural log of 1 over rad 3 plus the natural log of x plus 1 plus the square root of x squared plus 2x plus 4. So this could just become part of r plus c, just get absorbed in there. And then we could just factor this square root thing, well, to get to this form. And then it would match up completely with this form. So you have to be a little bit careful when using computer algebra systems to make sure that your answer is, what you would expect, but is not necessarily wrong. It could just be a completely different form of the exact same answer using different identities. Let's do another example where we use a computer algebra system to evaluate the integral of x times x squared plus 5 to the 8th dx. So we go back. Let's replace this with x times x squared plus 5 to the 8th. Okay. Let's see if it's going to behave this time. Nice. I'll make that a little bit bigger. Okay, so this is probably what we would get, I think, if we would do u substitution, right? We could let u equal x squared plus 5, and we would get the integral of x times x squared plus 5 to the 8th is equal to 1/18 x squared plus 5 to the 9th plus c, which matches what we would get. However, some calculators sometimes will only give you the answer in expanded form. So you might get an answer like this, where you have x to the 18th plus all these terms, blah, 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 and it looks really cumbersome and horrible. But you have to think to yourself, okay, well, this is not the only possible form. It could also look like this. Conversely, maybe you do only want the expanded form because that's more useful to you to plug into something. It depends. Let's use a cast to find this integral now. So I think we did this integral already in section 7.2. We saw that it equals, well, if we take sine to the 5th, cosine squared, it equals minus 1/3 cosine cubed plus 2/5 cosine to the 5th minus 1/7 cosine to the 7th plus c. So let's see if we get the same thing from our cast. So we do sine to the fifth and cosine to the second. And it looks very different. We have a cosine cubed, but we have a cosine 2x, cosine 4x. So let's pull this off. Notice that even if we were to go and look at alternate forms, even the alternate forms don't seem to match up with ours. So we suspect over here that there's some trig identities going on that's converting the cosine to the fifth and the cosine to the seventh into something in terms of cosine cubed and some double angle formula applied multiple times, maybe to get a quadruple angle. So again, you got to be a little bit careful about the alternate forms, because we know from what we did our answer is definitely correct, but we also trust Wolfram Alpha or Mathematica that this answer is definitely correct. So maybe it's worth exploring to see exactly how they managed to expand this out and with their different identities.